All right, so with this understanding, let's go back and let's write the algorithm, right? The Johnson's parallel algorithm. So this is with 1D distribution, right? Johnson SSSP with a 1D distribution, right? So again, you have vertices, edges, weights, and you have a root vertex, root source. So we've been using R and S interchangeably. So I'm going to start with the following. So I'm going to check if owner of the root is me, is my rank. Yeah. In that case, I need to set d bar of r equal to 0, right? And just insert r into the priority queue. Should I refer to this as PQI? I hope it's clear, right? That all these algorithms are executing on separate processes. So this code is executing separately on each processor, right? So each node will have its own set of vertices, only the local vertices, right? Of course, the vertex IDs are global because the adjacency list for every vertex points to other vertices which it does not own, right? So the vertex IDs are global, but the vertices that this processor is responsible for, it only has information about the local vertices, right? The adjacency lists, not all of them. So I'm just referring to PQI as the priority queue on process I, right? So I'm just assuming that, this entire thing is executing on processor I. So the same thing will be executing on all the processors, right? So we insert R into priority queue I if I am the owner. And now what do we do? For all V belonging to V, I'm going to set D of V equal to infinity, right? Okay. So just note, right? The only difference between D and D bar is D is kind of like a stable value that we are seeing. D bar is kind of like a more dynamic value, which is there in the priority queue. When a node gets settled, D bar is just copied into D. All right, now we are going to run our main loop. So how many iterations do I need to run for? I don't know. So I'll have to run an infinite loop, right? And I'll have to test inside, when I have to break. So we've already seen this before. Okay, what do I do now? Let me extract min from priority queue I. Yeah. So extract the min element. And for that min element, I'm going to set DUI equal to D bar of UI. Yes. Now, what do I need to do with this UI? I need to go and examine all its neighbors and, prepare messages and send to the owner, right? So for all neighbors V in the adjacency list of U. So look, I've been using some of this very loosely, right? But I hope you're fine with it. I sometimes call it, just refer to them as neighbors. Sometimes I call them as adjacent U, right? So this is very loose pseudocode. At the end of the day, it depends on what is the data structure you're using. Either you're using adjacency list, which is mostly the case, or you're using adjacency matrix. So you need to just code this appropriately, right? Depending on what is being used. All right, so what do I do for the neighbors? I send to the owner of V the message containing the vertex V to be visited and the new distance to it, DUI plus W UIV. Yeah, so just a tuple, right? That's what I'm sending to that. No. Again, I'm not getting into details. What you can do over here is you can first create buffers. So we've already seen this, right, in previous codes. So we already know how to do that. So I'm not going to revisit that again and again. So you can prepare buffers for each proc and then send in one shot. Practically, that's the way you would implement it, right? You wouldn't keep sending separate messages. Short messages are not efficient. All right, and now you basically receive messages. And what do you do with the received messages? For each received message. Let's say that the message received is v comma somebody sent a d of some vertex. Some processor must have settled some vertex x and v was a neighbor of x, right? So that's why I'm receiving this message. Is that clear? So v is local to me, right? V must be local to me. That's why I'm receiving this message. Okay. So what do I do now? The first thing you do is you check if v is in the priority queue. If v is in the priority queue, right, then you basically check if this new distance that you've received, dx plus wxv, is better than the current distance that's there in the priority queue. Yeah. If it is, then what do? You update d bar v. What does update involve here? It's in the priority queue, right? And you're updating the values. It's kind of equivalent to remove and reinsert, or you can adjust it locally, right? Essentially, it's a log number of elements, log n by p operation, right? That's the crux. Okay, so you update d bar v and you readjust in priority queue, right? That's what update actually means. Okay. If dx plus wxv is not less than d bar v, then what do? Nothing. You don't need to do anything. Yeah, then let it be. Okay. So this is where this ends. Now let's consider the case else, right? What does else mean? This means that v not in the priority queue. It was not in the priority queue to begin with. Okay, so if it wasn't in the priority queue, what do? Then you check if d of x. I'm writing this again just for the pseudocode sense. Actually, you will not be receiving d of x separately and wxv separately. You will be just receiving one value, right? I'm just writing this for clarity. If dx plus wxv, the received value, is less than d of v, then you need to go and check against the settled value. Is that clear? If it is not in the priority queue, this is the part where we may reactivate a settled vertex. Okay. So if d of x plus wxv is less than d of v, then what do? You basically, you set d bar of v equal to d of x plus wxv, right? The received value. And you insert v into the priority queue. Clear? Again, this is a log n by p operation, right? Because you have n by p vertices on each processor. So this is the part where you're reactivating a settled vertex, right? And next time it gets pulled out again, you'll again have to send messages to all its neighbors. So while it's in the priority queue, the value d may be outdated, right? It may not be of any significance. And we are not going to refer to it. We are only going to refer to d bar values, right? As long as it's in the priority queue. When it's out of the priority queue, we refer to the d values. When it's in the priority queue, we generally work with the d bar values, right? That's the crux. All right, that's about it, right? Anything else that remains? Now, when do you terminate? So again, you have to check for termination. How do you check for termination? We've already done this many times, so let's not do it again. Everybody examines their priority queues. And if everybody's priority queue is empty, right, you just exchange the number of elements in the priority queue. You do a reduce operation or all reduce operation. So everybody comes to know what is the total number of elements in all the priority queues put together. If that is 0, then you exit. Otherwise, you continue on. So in this setting, what did we initialize? We initialized dv equal to infinity for everybody. So that's kind of like saying that everybody is settled, right? The way we initialized it, we settled everybody to begin with the value of infinity, except for, of course, the root. But that's fine. When they get the first message, they will reactivate again, right? We could have gone with the other approach as well, which was what we've been doing earlier, that, add everybody to the priority queue first. So everybody is kind of active and then keep on operating, right? That's the other way to do it. So all the values in the priority queue would have been infinity on many processors except for the root. And when you do the extract min operation and you get infinity, what do you need to do? Don't extract it out of the priority queue, leave it there, right? It's equivalent to that, whatever you feel more comfortable with implementing. Okay.